Why is light speed so slow? That question sounds strange at first. Light moves at about 300,000 kilometers every second. It circles the Earth 7 times in a single second. It reaches the Moon in just over 1 second. It reaches the Sun in 8 minutes. In everyday life, that feels instant. Light stands at the top of the speed ladder. Physics describes it as the upper limit written into space itself. Nothing with mass travels faster. Rockets, planets, and even the fastest particles remain below it. Light moves with steady certainty, untouched by hesitation. So how could something so fast ever feel slow? The shift begins when distance grows beyond anything familiar. If you enjoy exploring big questions like this in a calm and unhurried way, you're always welcome to subscribe. And feel free to share where you're listening from. It's always nice to imagine this conversation stretching gently across the world, maybe one day across the universe as well. Light reaches the Sun in 8 minutes. That feels manageable. 8 minutes is the length of a quiet break. Yet the nearest star beyond the Sun sits about 4.24 light years away. Even light itself needs more than 4 years to cross that distance. A message sent at light speed would arrive years later. A reply would take years again. One simple exchange stretches across nearly a decade. Distance reshapes the feeling of speed. The effect becomes even clearer inside our own galaxy. The Milky Way spans about 100,000 light years from one side to the other. Light, moving at the fastest speed possible, would need 100,000 years to cross it. Recorded human history covers about 5,000 years. Civilizations could rise and fade 20 times, while a beam of light quietly traveled from one edge of our galaxy to the other. That comparison carries weight because it is measurable. 100,000 years. 20 cycles of civilization. The number remains steady. The scale grows beyond instinct. Then the view expands again. The Andromeda Galaxy lies about 2.5 million light years away. Light leaving Andromeda today would arrive here long after present cultures and languages have transformed beyond recognition. The journey would span stretches of time that dwarf familiar history. The observable universe extends even farther, roughly 93 billion light-years across. The universe itself is about 13.8 billion years old. Light has traveled since the beginning. Even so, it has not crossed that entire span. There are regions of space whose light has never reached us. There are galaxies so distant that the expansion of space carries them farther away with every passing moment. The fastest thing in existence meets boundaries in the vastness of the cosmos. On Earth, light feels immediate because Earth is small. A planet only about 12,700 kilometers wide poses little challenge to a speed of 300,000 kilometers per second. Across such modest distances, light appears effortless. You can think of it like a powerful fire hose. Spray it into a cup, and the cup fills instantly. It feels unstoppable. Spray that same hose into the ocean, and the water seems to disappear. The flow has not slowed. The container has simply grown beyond proportion. Light behaves in a similar way. Across a planet, it feels immediate. Across a galaxy, it feels patient. Our daily experience reinforces that impression. Rooms brighten instantly. Sunlight floods the horizon without delay that our senses can measure. human intuition formed around short distances and short waits. We evolved among forests, rivers, and mountains. Our mind measures in footsteps and heartbeats. Against those scales, light feels absolute. Yet when distance expands from kilometers to light years, perception shifts. The speed remains the same. The distances expand into numbers that stretch far beyond ordinary reference points. What once felt instant begins to feel gradual. What once felt limitless begins to reveal horizons. The question then carries a quiet depth. Why does the ultimate speed feel patient across the universe? The answer rests in scale. Speed alone holds meaning only when paired with distance. On small stages, light dominates. On cosmic stages, the size of the arena reshapes the impression entirely. Light never slows. It moves with unwavering rhythm through empty space. The universe simply extends farther than intuition expects. When the fastest possible motion encounters distances measured in millions and billions of light years, the contrast invites reflection. The speed remains extraordinary. The vastness redefines extraordinary. And that is where the question begins. When we speak about the speed of light, we are speaking about a very specific number. Light travels at about 300,000 kilometers every single second. In miles, that is about 186,000 miles per second. The number itself is difficult to hold in the human mind. It moves far beyond everyday experience. 1 second feels short. It is the length of a quiet pause. It is the time it takes to take one breath. In that single second, light could circle the entire Earth about 7 times. It could leave one side of the planet and return again and again before you finish blinking. If you turn on a lamp, the room fills instantly. When the sun rises, daylight seems immediate. There is no visible travel, no waiting, no delay that the human senses can notice. For most daily life, light feels present the moment it begins. This speed is so extreme that it sets the limit for everything else. Physics describes it as a boundary built into the structure of space itself. Objects that have mass require energy to move. As they move faster, they require more energy. As they approach light speed, that energy demand rises sharply. The closer something moves toward that limit, the more effort it requires to gain even a small increase in speed. Light behaves differently because it has no mass. It does not carry weight in the way a rock or a planet does. Because of this, it moves at the maximum speed allowed by the universe. This is why it becomes the cosmic speed limit. Nothing carrying mass can reach or pass it. This number, 300,000 kilometers per second, feels enormous when compared to everything familiar. The fastest passenger jets move at around 900 kilometers per hour. Even the fastest spacecraft ever built move at only a small fraction of light speed. The gap between our machines and this natural limit is vast. To understand it more clearly, we can compare it to common distances. The Moon is about 384,000 kilometers away from Earth. Light takes about 1.3 seconds to travel that distance. That means when you look at the Moon, you see it as it was just over 1 second ago. The delay is small, yet it exists. The Sun is much farther. It sits about 150 million kilometers away. Sunlight takes about 8 minutes to reach Earth. When you feel warmth on your skin, you are feeling energy that began its journey 8 minutes earlier. The sun you see in the sky is slightly in the past. These numbers begin to stretch the sense of immediacy. 8 minutes is long enough to make a cup of tea. It is long enough to sit quietly and watch a clock. Even at light speed, distance introduces waiting. If you move farther out into the solar system, the delay grows. Light takes about 43 minutes to reach Jupiter from the Sun. It takes over 4 hours to reach Neptune. Signals sent to distant spacecraft must cross these gaps. Engineers must account for those delays when communicating across space. This steady pace never changes. Light does not hurry. It does not slow down. It moves with the same constant rhythm everywhere. In empty space, in the atmosphere, near planets, and between stars, its speed remains fixed. This constancy is part of what makes it so important. The speed of light connects space and time. It helps define how distances are measured. A light year, for example, is the distance light travels in 1 year. That distance is about 9.46 trillion kilometers. The term blends speed and time into one idea. When we hear that a star is 4 light years away, we are hearing both a measure of distance and a measure of time. The light leaving that star will need 4 full years to reach us. That connection between motion and waiting begins to reshape how speed feels. On Earth, light appears instant because Earth is small. Our daily distances are tiny compared to the distances of space. The planet itself is only about 12,700 kilometers wide. Light crosses that width in a fraction of a second. Against such small scales, light feels boundless. Speed itself never changes. Only the distances change. As we widen our view beyond Earth, that same fixed speed begins to meet distances that stretch into years, centuries, and millennia. The number remains the same. The effect feels different. This is the quiet shift that prepares us for the larger picture. The speed of light is extreme. It is steady. It is built into the fabric of the universe. It dominates every small scale we experience. Yet, as the distances grow, the meaning of that speed begins to evolve. What once felt instant begins to feel measured, and measured speed placed against immense distance begins to feel very different. Light moves quickly. That much feels clear. Yet what makes it even more unusual is that its speed is not simply impressive. It is fixed. It does not change from place to place. It does not depend on who is watching. It stands as a constant woven into the structure of reality itself. In physics, this number is often written as a simple letter, c. That letter represents about 300,000 kilometers per second. More than just a measurement, it acts like a boundary line. Nothing carrying mass crosses it. If you throw a ball, it moves at some speed. If you push it harder, it moves faster. If you push it even harder, it moves faster still. That pattern feels simple. More effort leads to more speed. Objects in space follow that same rule at first. Rockets burn fuel and accelerate. Spacecraft gather momentum. Particles in accelerators are pushed to incredible velocities. As they move faster, they gain energy. Yet something strange happens as objects approach light speed. The closer they move toward that limit, the harder it becomes to increase their speed. Each small gain demands far more energy than the last. Near light speed, the energy required grows enormously. It becomes so extreme that reaching the exact speed of light would require infinite energy. Infinite energy does not exist in practical terms. No engine can provide it. No explosion can generate it. The limit remains firm. Light itself moves at that boundary because it does not carry mass. Photons, the particles of light, do not have weight in the way matter does. Because of this, they travel at the maximum allowed speed of the universe from the moment they are created. They do not accelerate up to it. They simply move at that speed. This fixed limit shapes more than motion. It shapes space and time together. When something moves very quickly, close to light speed, time begins to behave differently. Clocks moving at high speeds tick more slowly compared to clocks at rest. Distances in the direction of motion begin to shorten. These effects are small at everyday speeds. At speeds near light, they become noticeable. This means light speed is not just about how fast something travels. It connects deeply to how time flows and how distances are measured. It ties space and time into a single structure, often called spacetime. Because light speed is constant, it allows cause and effect to remain ordered. Events unfold in sequence. Signals travel outward at a steady pace. Information cannot leap instantly from one side of the universe to the other. That boundary preserves structure. If there were no maximum speed, the order of events could blur. Causes and effects could overlap unpredictably. The steady pace of light keeps the universe coherent. It also defines what can be known. When a star shines, its light spreads outward in all directions. That light travels at the same fixed speed. If the star is 10 light years away, we see it as it was 10 years ago. If it is 1 million light years away, we see it as it was 1 million years ago. The constant speed of light turns distance into time. Every time we look into the night sky, we are looking into the past. The farther we look, the older the light becomes. This quiet rule is built entirely on the steadiness of light's motion. Even our units of measurement reflect this importance. A light year is not a unit of time, even though it sounds like one. It is a unit of distance. It represents how far light travels in 1 year. That distance is about 9.46 trillion kilometers. The idea itself blends motion and duration into a single concept. This steady limit also applies to all forms of light, not only visible light. Radio waves, X-rays, gamma rays, and infrared light all travel at the same speed in empty space. They differ in energy and wavelength, yet their pace remains identical. That sameness reinforces the idea of light speed as a universal boundary. The speed does not stretch or shrink depending on direction. It does not depend on how fast the source is moving. Whether a flashlight is turned on while standing still or while riding in a spacecraft, the light still moves at the same speed once it leaves the source. This property surprised scientists when it was first discovered. It reshaped how motion itself was understood. Instead of speed adding up in simple ways, light maintained its constant rhythm. So when we speak about light as the cosmic speed limit, we are describing more than a high number. We are describing a structural feature of reality. It acts like the edge of a map. It defines the maximum rate at which influence and information can travel. Nothing outruns it. Nothing with mass catches it. Yet even this ultimate limit, fixed and unwavering, must cross distances measured in years, centuries, and millennia. The rule is firm. The speed is constant. The scale, however, continues to grow. To understand how speed begins to feel different, it helps to start close to home. The Moon orbits Earth at an average distance of about 384,000 kilometers. That number feels large when spoken aloud. It is far beyond any journey a person could make on foot or by plane. Yet for light, that distance is brief. Light travels from the Moon to Earth in about 1.3 seconds. When you look up at the Moon, you are seeing it as it was just over 1 second ago. The delay is small enough that it feels immediate. If something changed on the Moon, you would not notice the difference until light had crossed that gap. Even so, 1 second feels like almost nothing. The Sun introduces a new scale. The average distance between Earth and the Sun is about 150 million kilometers. Light covers that distance in about 8 minutes. When you feel sunlight warming your face, that energy began its journey 8 minutes earlier. The sun you see shining in the sky is slightly in the past. 8 minutes is long enough to brew coffee. It is long enough to sit quietly and watch clouds drift. It is long enough to think about what 8 minutes really means. The sun feels close in the sky. It dominates the day. It rises and sets with steady rhythm. Yet even here, light requires measurable time to cross the space between star and planet. This delay becomes clearer when we imagine events. If the sun were to suddenly change in brightness, Earth would continue to receive the old sunlight for 8 full minutes. The information about that change would travel outward at light speed. Only when the new light arrived would we notice the difference. This quiet waiting introduces a subtle shift in perspective. Light moves incredibly fast, yet distance still creates separation between event and awareness. When we look farther into the solar system, the pattern continues. Jupiter sits much farther from the Sun than Earth does. Light from the Sun takes about 43 minutes to reach Jupiter. Signals sent from Earth to spacecraft near Jupiter take tens of minutes to arrive. Engineers cannot control those spacecraft in real time. They must plan carefully, knowing that commands travel with delay. Neptune, the outermost major planet, sits even farther. Light takes over 4 hours to travel from the Sun to Neptune. A signal sent from Earth to a spacecraft near Neptune must cross that distance and then return. A simple exchange can span most of a day. The speed of light remains constant throughout all of this. It does not slow down between planets. It does not hesitate in empty space. It simply moves at its steady pace. The growing delay comes entirely from the widening distance. Within the solar system, these waits feel manageable. Minutes and hours remain within human understanding. We can imagine waiting an hour. We can picture waiting a few hours. Yet even here, light has begun to reveal that space is larger than instinct expects. The Moon and the Sun provide a bridge between everyday life and cosmic scale. The Moon shows how quickly light crosses modest distances. The Sun shows that even the central star of our system sits 8 minutes away in time. When you watch a sunrise, you are watching something that already happened. When you observe a solar flare, you're observing an event that occurred minutes earlier. The present and the slightly past coexist quietly in every beam of light. This idea grows stronger as distance grows. On Earth, light feels instant because the planet is small. The diameter of Earth is about 12,700 kilometers. Light crosses that width in a fraction of a second. From one side of the planet to the other, the delay is nearly invisible. Against such small distances, light appears absolute. It dominates scale. It erases weighting. The moon begins to stretch that illusion. The sun stretches it further. Each step outward adds measurable time. Each added kilometer introduces delay. The pattern is steady and simple. Speed remains the same. Distance increases. Weighting grows. The moon and the sun serve as the first gentle reminder that even the fastest possible motion requires time to cross space. The gap between event and observation begins small. It expands gradually as we move outward. What feels immediate at planetary scale begins to feel patient at stellar scale. And this quiet patience will grow even more as we leave the solar system behind. Leaving the solar system changes the feeling of distance almost immediately. Beyond our Sun, the closest star is called Proxima Centauri. It sits about 4.24 light-years away from Earth. That number sounds simple at first. 4 years does not feel overwhelming. It feels manageable. It fits within the span of a college degree. It fits within a short chapter of a human life. Yet a light year is not a small unit. 1 light year is the distance light travels in 1 full year. That distance is about 9.46 trillion kilometers. When we say Proxima Centauri is 4.24 light-years away, we are saying its light must travel for more than 4 years at 300,000 kilometers per second before reaching us. The speed remains extreme. The waiting becomes real. If you were somehow able to travel at the speed of light, you would still need more than 4 years to reach that nearest star. That journey would be longer than most space missions ever attempted. It would stretch longer than many technological cycles on Earth. During those 4 years, entire industries could transform. Languages could shift. Political landscapes could evolve. And that is just the nearest star. The gap between stars inside our own neighborhood is vast. The Sun and Proxima Centauri are separated by trillions upon trillions of kilometers of mostly empty space. Between them lies no bright cluster of activity, no chain of stepping stones, just quiet vacuum. Light crosses that vacuum steadily. It does not accelerate. It does not slow. It moves at its constant pace. Yet 4 years is long enough to begin feeling the weight of separation. If you imagine sending a simple message to a planet orbiting Proxima Centauri, the signal would take over 4 years to arrive. If someone there replied immediately, their response would take 4 more years to return. A single exchange becomes an 8-year conversation. A child could grow from early school age to adolescence between question and answer. Communication slows into patience. This delay reshapes how connection would feel across the stars. On Earth, messages cross oceans in fractions of a second. We speak across continents without noticing distance. Across interstellar space, the fastest possible signal carries time with it. When you look at Proxima Centauri in the night sky, you are not seeing it as it is now. You are seeing it as it was more than 4 years ago. If something changed there today, you would not know for years. Every glance becomes a window into the past. This pattern holds for every star beyond our solar system. Each point of light represents distance measured in years of travel. Some stars visible to the eye are dozens or hundreds of light years away. Their light began its journey before many of us were born. The idea begins gently. 4 years does not feel endless. Yet when you remember that this is the closest star, perspective shifts. If even the nearest neighbor sits more than 4 years away at light speed, then the broader galaxy must stretch far beyond everyday instinct. The nearest star is not a short trip. It is a multi-year crossing at the fastest speed possible, and that is only the first step outward. This realization introduces a quiet expansion of scale. The solar system, though large, feels compact compared to the space between stars. Light crosses the solar system in hours. It crosses the gap to the nearest star in years. The difference between hours and years marks a turning point in perception. We often imagine stars as clustered tightly in the night sky. From Earth, they appear sprinkled closely together. Yet that appearance hides immense separation. Each star floats alone, separated from its neighbors by trillions of kilometers of darkness. Light bridges those separations slowly, steadily, and without deviation. 4 years for the nearest star. That number rests quietly at the edge of comprehension. It is small enough to imagine, yet large enough to feel distant. It signals the beginning of a new scale, one measured not in minutes or hours, but in years of uninterrupted motion. And as we continue outward beyond this nearest neighbor, those years will stretch into tens of thousands and then millions. The journey has only just begun. Imagine, for a moment, that someone lives on a planet orbiting Proxima Centauri. You decide to send them a message. You aim a powerful transmitter toward that distant star. The signal leaves Earth at the fastest speed possible. It travels at light speed, steady and constant, crossing trillions of kilometers of empty space. It will take more than 4 years to arrive. For 4 full years, your message moves silently through darkness. It passes no cities, no oceans, no mountains. It moves through near-perfect vacuum, untouched and uninterrupted. Only after those years have passed does it finally reach its destination. Now imagine they reply immediately. Their answer begins its journey back toward Earth, again at light speed. It will take 4 more years to cross the same gap in reverse. One question becomes an 8-year exchange. You send a greeting in 2026. You receive the reply in 2034. A single follow-up question would stretch the conversation into the 2040s. A back-and-forth discussion becomes something measured in decades. Real-time conversation disappears. On Earth, we are used to immediacy. Messages cross oceans in fractions of a second. Video calls connect continents without noticeable delay. We speak, and we hear a response almost instantly. Our sense of communication depends on short gaps between action and reaction. Across interstellar space, that gap becomes vast. Even if technology were perfect, even if energy were unlimited, the delay would remain. It is not a technical problem. It is a structural one. The speed limit of the universe sets the pace. If someone near Proxima Centauri asked you a simple question today, you would not hear it for over 4 years. By the time you replied and they heard your answer, Nearly a decade would have passed since the original thought was formed. In that time, lives change. People grow older. Circumstances shift. History unfolds. Communication across the stars would feel less like conversation and more like sending letters across generations. This delay grows quickly as distance increases. A star 10 light-years away would introduce a 20-year round-trip exchange. A star 100 light-years away would stretch a simple conversation across 2 centuries. The farther the distance, the longer the silence between words. The speed of light remains steady. The delay is not caused by weakness or inefficiency. It is caused by scale. The space between stars is simply too large for immediacy. This reshapes what connection means. If civilizations exist elsewhere in the galaxy, they are separated not only by distance, but by time. Even if both sides are curious, even if both sides are listening, the gap between message and reply could span lifetimes. In our solar system, engineers already work within these limits. Signals to Mars can take several minutes to arrive, depending on its position. Commands sent to spacecraft near Jupiter take much longer. There is no instant correction, no immediate response. Everything unfolds with patience. Multiply that patience by years, then by decades, and eventually by centuries. The scale of the galaxy turns conversation into something slow and deliberate. When you look at the nearest stars, you are seeing them as they were years ago. If a civilization there were to send a signal tonight, it would travel steadily toward Earth. It would cross the dark space between stars at 300,000 kilometers per second. It would move without pause. Yet it would still need years to arrive. The universe does not rush. In this way, space slows communication deeply. It does not silence it. It simply stretches it. Words take years to cross the gap. Replies take years more. The silence between messages becomes part of the exchange. Across such distances, time becomes woven into every interaction. Light carries information faithfully, yet it cannot erase the waiting. The fastest signal possible still moves with quiet patience across interstellar darkness. And as we step farther outward into the galaxy itself, those years will grow into numbers that extend far beyond personal experience. The silence will stretch even longer. Now step back even further. So far, we have spoken about planets and nearby stars. We have measured distance in minutes and then in years. Yet all of those examples sit within a small region of something much larger. That larger structure is our galaxy. The Milky Way is the vast spiral system of stars that contains our Sun. When you look up at the night sky from a dark location and see a faint band of light stretching across the horizon, you are seeing a small portion of it from the inside. That soft glow is made of billions of distant stars packed together in the galactic disk. Our galaxy spans about 100,000 light-years from one side to the other. That number deserves to be said slowly. 100,000 light-years wide. A light-year is the distance light travels in 1 year. So if light began at one edge of the Milky Way and traveled straight across to the opposite edge, it would need 100,000 years to complete the journey. 100,000 years. Recorded human history stretches back roughly 5,000 years. The earliest cities, writing systems, and organized societies emerged within that window. If light began crossing the Milky Way when the first pyramids were built, it would still be only a small fraction of the way across today. It would take 20 entire stretches of recorded human history for light to cross our galaxy. That comparison is steady and measurable. The speed remains unchanged. The scale expands beyond ordinary experience. When we imagine the galaxy, we often picture a swirling spiral of stars, luminous and elegant. From afar, images of spiral galaxies look compact and graceful, yet those images hide enormous separation between stars. Inside the Milky Way are hundreds of billions of stars. Between each one lies immense emptiness. The Sun sits about 27,000 light-years from the center of the galaxy. Even that distance alone is many times larger than the gap between us and Proxima Centauri. If light began at the galactic center and traveled outward toward us, it would need 27,000 years to arrive. That means the light reaching us today from the central regions of our galaxy began its journey long before the rise of modern civilization. Light moves steadily. The waiting grows immense. To cross from one spiral arm of the galaxy to another can require tens of thousands of years of uninterrupted motion. Even at the fastest speed allowed by physics, the Milky Way resists quick traversal. The galaxy does not shrink in response to speed. It holds its scale. When we speak about traveling at light speed, we often imagine something immediate and triumphant. Yet across galactic distance, even that ultimate velocity feels patient. The numbers no longer fit within a single lifetime. They stretch across eras. 100,000 years is longer than the entire span of agriculture. It is longer than written language. It is longer than almost every structure built by human hands has existed. Light would need all of that time just to cross our galactic home. This is the moment when the feeling shifts. On Earth, light feels absolute. Across the solar system, it feels swift. Between nearby stars, it feels committed. Across the Milky Way, it feels measured. The scale of the galaxy transforms speed into duration, and the Milky Way is only one galaxy among many. When you look at the faint band of light overhead, you are looking across tens of thousands of light years. Each star you see is separated from its neighbors by distances measured in years of travel. The galaxy holds together through gravity, yet its parts remain widely spaced. Light crosses it faithfully, without pause. It simply requires time. The number 100,000 carries weight because it exceeds instinct. It exceeds history. It exceeds memory. Even light, moving as fast as the universe allows, cannot compress that span into something brief. The Milky Way stretches wider than comfort, and beyond its edges lie other galaxies, separated by even greater distances. The scale continues to grow. Now step outside our galaxy. The Milky Way feels enormous when viewed from within. 100,000 light-years across already stretches beyond familiar timescales. Yet the Milky Way is only one galaxy among hundreds of billions scattered across the observable universe. The nearest large galaxy to us is called Andromeda. Andromeda sits about 2.5 million light-years away from Earth. That number marks another shift in scale. We have moved from thousands of light-years to millions. Light leaving Andromeda today will take 2.5 million years to reach us. When you look at Andromeda through a telescope, you are seeing light that began its journey long before modern humans walked the earth. 2.5 million years ago, early human ancestors were just beginning to use simple stone tools. Entire branches of human evolution have unfolded in the time it took that light to cross intergalactic space. The galaxy we observe tonight is a portrait from deep time. This pattern repeats for every galaxy beyond our own. Each one floats in vast stretches of space, separated by distances measured not in years, but in millions of years of travel at light speed. Between the Milky Way and Andromeda lies mostly empty space. There are small dwarf galaxies, scattered stars, and faint streams of matter. Yet the dominant impression is emptiness. Light moves steadily across that gap, yet the distance stretches the journey across geological ages. Even at the fastest speed possible, crossing from one galaxy to another becomes a multi-million-year passage. If you imagine departing from Earth at light speed toward Andromeda, your arrival would occur in a future so distant that present civilizations would feel ancient. Languages would shift beyond recognition. Continents would subtly rearrange. Climate cycles would rise and fall. The journey itself would last longer than the time since early human ancestors first shaped stone tools. This is where time and distance begin to blend into one experience. A light year already merges speed and duration. 1,000,000 light years expands, that merging into something that dwarfs human timelines. When astronomers observe distant galaxies, they are observing history. The farther the galaxy, the older the light. Some galaxies visible through powerful telescopes appear as they were billions of years ago. Their light began traveling before Earth even formed into its present shape. Light becomes a messenger from the distant past. And yet, it moves at the same steady pace it always has. Nothing about its speed changes. The only difference is the span it must cross. Galaxies themselves are not tightly packed together. They are scattered across enormous volumes of space. If the Milky Way were reduced to the size of a coin, the nearest large galaxy would still be meters away. The scale between galaxies dwarfs the scale within them. Intergalactic space contains far fewer stars than the interiors of galaxies. It is darker and emptier. Light traveling between galaxies crosses long stretches without encountering anything at all. 2.5 million years for Andromeda, tens of millions of years for galaxies farther out, hundreds of millions, then billions. The numbers expand quietly, without drama. The pattern remains simple. Speed is constant. Distance grows. When we look up and see the faint smudge of Andromeda in the night sky, we are seeing ancient light that began traveling long before human memory. That galaxy continues to exist and evolve in the present moment. Yet the version visible to us belongs to the deep past. The farther outward we look, the deeper into time we see. Time and distance stretch together across intergalactic space. Even at light speed, crossing from one galaxy to another demands patience measured in millions of years. The universe does not compress itself for convenience. Its structure unfolds across scales that resist quick traversal. And as we widen our view beyond nearby galaxies, the distances expand further still, until they approach the limits of what light has had time to cross since the beginning of the universe. The scale continues outward. Now widen the lens completely. So far, we have stepped outward in layers. From Earth to the Moon, from the moon to the sun, from the sun to nearby stars, from stars to the Milky Way, from the Milky Way to Andromeda. Each step has expanded distance by orders of magnitude. Yet even all of that remains within what we can observe. The observable universe is the region of space from which light has had enough time to reach us since the beginning of cosmic history. Its estimated diameter is about 93 billion light-years. That number stretches beyond instinct. The universe itself is about 13.8 billion years old. Light has been traveling since the earliest moments after the beginning. Even so, the region we can see spans about 93 billion light-years across. This might sound confusing at first. If the universe is 13.8 billion years old, how can the observable region be wider than 13.8 billion light-years? The answer rests in expansion. As light traveled across space for billions of years, space itself continued to stretch. Galaxies drifted farther apart. The distance between starting point and arrival point grew during the journey. What began as a smaller separation expanded over time. The result is that the edge of what we can observe lies far beyond 13.8 billion light-years away. Light has not crossed the entire universe. It has only crossed the portion that had time to send signals our way. Everything we see exists within that boundary. When we look at extremely distant galaxies, we are seeing light that has traveled for billions of years. That light began its journey when the universe was young. It moved steadily across expanding space, finally arriving at our telescopes. Yet beyond that observable horizon lies more universe. There are regions so distant that their light has not yet reached us. There are places so far away that, even if they emitted light at the beginning of time, it has not had enough time to cross the expanding space between us. And there are regions that will never be visible to us at all. Because space continues to expand, some galaxies are carried away from us so quickly that their light can no longer close the distance. Even moving at the maximum possible speed, light cannot overcome the stretching of space in certain regions. Those galaxies exist, they shine, yet their future light will never reach Earth. The speed of light defines the edge of our awareness. Everything inside the observable universe lies within a sphere centered on us. Not because we occupy a special position, but because light from those regions has had enough time to arrive. Another observer in a distant galaxy would have their own observable universe centered around them. Their horizon would include regions we cannot see and exclude regions we can. The observable universe is not the entire universe. It is simply the portion connected to us by the travel time of light. 93 billion light-years across. That number reflects how far light has managed to travel and how much space has expanded during its journey. It represents the boundary between what can be known through observation and what lies beyond direct reach. The fastest thing in existence has drawn a circle around our awareness. Everything beyond that circle remains unseen, not because it does not exist, but because light has not bridged the gap. This is where the question deepens. Light is unimaginably fast. It crosses planets in fractions of a second. It crosses galaxies in tens of thousands of years. Yet even after billions of years of uninterrupted motion, it has not crossed the entire universe. The limit is not in the speed itself. The limit is in scale. The observable universe shows that light's pace, though extreme, still encounters horizons. It defines what can be connected, what can be measured, what can be studied. Beyond that horizon lies more structure, more galaxies, more history. Yet they remain beyond contact. The speed of light becomes the boundary of knowledge. And within that boundary, time and distance continue to intertwine as we look further back toward the beginning itself. Now bring time fully into view. The universe is about 13.8 billion years old. That number represents the time that has passed since the earliest known stage of cosmic expansion. It marks the beginning of everything we can observe, the starting point from which light first began to travel freely through space. For billions of years, light has been moving. The oldest light we can detect today is called the cosmic microwave background. It began traveling when the universe was still very young, roughly 380,000 years after its earliest expansion. Before that time, the universe was too dense and hot for light to move freely. Once it cooled enough, light could finally travel outward without constant interference. That ancient light has been crossing space for more than 13 billion years. When we detect it with sensitive instruments, we are seeing a faint echo from the early universe. We are observing a signal that began long before stars, planets, or galaxies formed in their present shapes. The speed of light connects us directly to that distant past. Every time we look deeper into space, we look further back in time. A galaxy 1 billion light years away appears as it was 1 billion years ago. A galaxy 10 billion light years away appears as it was 10 billion years ago. Distance becomes a timeline. The farther the light travels, the older the image becomes. This relationship between distance and time exists entirely because light moves at a fixed speed. If light traveled instantly, we would see the universe as it is now, everywhere at once. There would be no delay. There would be no layered history. Everything would appear in a single moment. Instead, the steady pace of light creates a natural archive. We see nearby objects almost as they are now. We see distant objects as they were long ago. The universe unfolds in layers of time, stacked across billions of light years. This layered view reveals something important. Even though the universe is 13.8 billion years old, we cannot see events that occurred before light had time to reach us. The beginning itself remains partially hidden behind the limits of light's travel. The age of the universe and the speed of light are linked. Light has had 13.8 billion years to move outward from its earliest sources. During that time, space has expanded. Galaxies have drifted farther apart. The regions from which light could reach us have stretched into a sphere about 93 billion light years across. That sphere marks our observable boundary. The age of the universe sets how long light has been traveling. The expansion of space stretches the distances light must cross. Together, they determine what we can see. When astronomers observe extremely distant galaxies, they are not seeing those galaxies as they exist now. They are seeing them in youth. Some of the galaxies observed at great distances appear small and irregular, still forming their structure. Their light left when the universe was only a fraction of its current age. In this way, light connects present observation with ancient events. The steady speed of light allows us to study cosmic history. Yet it also limits how far back we can look. Beyond a certain point, there was a time when light could not travel freely. Before that era, the universe was opaque. The age of the universe defines the maximum amount of travel time available. Light cannot show us anything older than the time it has had to move. Even at the fastest speed possible, time remains the governing factor. The universe has been expanding for 13.8 billion years. Light has been moving since the early stages of that expansion. Still, there are regions whose light has not yet reached us, and may never reach us because space continues to stretch. Time and distance are not separate in this context. They merge into one framework. When we speak about a galaxy being 10 billion light-years away, we are speaking about both distance and time. The number carries both meanings simultaneously. The age of the universe gives light its opportunity to travel. The speed of light sets how far that opportunity extends. The result is a cosmic map drawn not only across space, but across billions of years. Light moves steadily through expanding space. Time passes, galaxies drift. The observable region grows. Even so, the ultimate speed cannot erase the reality that the universe is vast and aging at the same time. Speed remains constant. Time continues forward. Distance expands. Together, they shape what can be known. After moving through billions of light years and millions of years of travel time, it helps to return to something simpler. Why does light feel so fast to us? The answer begins with scale. Human beings evolved on Earth. We learned to measure distance in steps, in meters, in the length of a field or the width of a river. We measure time in heartbeats, in seconds, in the turning of days. Our sense of speed formed in a world of walking, running, sailing, and eventually flying. On those scales, light feels absolute. If you clap your hands, the room brightens instantly when you flip a switch. If you step outside at sunrise, daylight floods the horizon without delay that your senses can detect. The distances involved are small compared to light speed. Earth itself is only about 12,700 kilometers wide. Light crosses that entire width in a fraction of a second. From one side of the planet to the other, the travel time is so brief that it feels like no time at all. Because of this, our intuition labels light as instant. Compare that to walking. A person walking at a steady pace covers about 5 kilometers per hour. Crossing a city takes time. Crossing a country takes days. Even flying across oceans requires hours. Against those familiar speeds, light seems limitless. A passenger jet travels around 900 kilometers per hour. Even the fastest spacecraft humans have launched move at only a tiny fraction of light speed. The gap between our experience and light's motion is enormous. So when we hear that light moves at 300,000 kilometers per second, the number overwhelms ordinary comparison. It dwarfs everything we know. But our intuition rarely considers cosmic distance. We do not instinctively imagine 4.24 light-years. We do not picture 100,000 light-years. We do not naturally grasp millions or billions of light-years. Those numbers exceed everyday context. Our brains are comfortable with scales that fit inside landscapes. We understand mountains. We understand oceans. We understand the size of a continent. Beyond that, imagination becomes more abstract. This mismatch shapes perception. Light feels fast because our reference points are small. We judge speed based on how quickly something crosses a familiar space. Light dominates every familiar space we have ever known. It crosses rooms instantly. It crosses cities in microseconds. It crosses Earth in a blink. When the stage remains small, the speed feels overwhelming. Yet when the stage expands to the size of a galaxy, our instincts fail to adjust. A galaxy spanning 100,000 light-years does not fit inside intuition. Even the number 100,000 begins to lose texture at that scale. The difference between 1,000 and 100,000 becomes hard to feel. The mind struggles to anchor numbers that large to lived experience. Because of this, we continue to carry our Earth-based intuition into cosmic discussion. We assume that the fastest speed possible should conquer any distance with ease. But scale changes the equation. Imagine measuring speed on a small racetrack. A runner crossing it in seconds appears swift. Move that same runner onto a continent, and the impression shifts. The runner has not slowed. The distance has grown beyond proportion. In the same way, light remains constant. The universe expands beyond proportion. Human perception evolved within narrow boundaries. We are adapted to notice delays measured in seconds. We are sensitive to sounds and sights that arrive within fractions of a second. That sensitivity serves survival on Earth. Interstellar distances never shaped our instincts. As a result, light feels instantaneous because our frame of reference is local. It is built from daily experience on a small planet orbiting an average star. When that frame widens to include galaxies and cosmic expansion, intuition lags behind. Light does not become slower. Our expectations become misaligned. We expect dominance because we compare light to cars and rockets. We rarely compare it to tens of thousands of light years. When we do, the contrast reveals itself quietly. The ultimate speed still requires time when distance becomes immense. Our intuition is grounded in the local. The cosmos operates on the immense. The feeling that light is slow arises not from any weakness in light, but from the enormous scale of the universe itself. And once that scale settles into the mind, perception begins to shift. At the center of this question lies a simple tension. Speed only has meaning when paired with distance. A number by itself does not tell the whole story. 300,000 kilometers per second sounds enormous. It is enormous. Yet that number becomes meaningful only when we ask a second question. 300,000 kilometers per second across how much space? On a small stage, that speed feels absolute. Light crosses a room instantly. It crosses a city in a fraction of a second. It crosses Earth in the time it takes to blink. Against distances measured in meters or kilometers, light day dominates so completely that delay disappears from perception. But increase the stage and the impression shifts. A car moving at highway speed feels fast within a city. On a journey across a continent, that same speed begins to feel modest. The car has not slowed. The continent has introduced scale. Light behaves the same way. Across Earth, light feels instant. Across the solar system, it feels swift. Across the gap to the nearest star, it feels patient. Across the Milky Way, it feels enduring. Across intergalactic space, it begins to feel almost still. The speed remains unchanged in every case. What changes is the distance it must cross. This is the core tension. We often focus on speed alone. We treat it as if it should conquer any separation. Yet speed and distance exist in partnership. Remove distance, and speed appears infinite. Increase distance, and even extreme velocity acquires duration. The universe expands scale in dramatic steps. The moon sits hundreds of thousands of kilometers away. The sun sits hundreds of millions of kilometers away. The nearest star sits trillions of kilometers away. The galaxy stretches across 100,000 light years. Nearby galaxies sit millions of light years away. The observable universe spans tens of billions of light years. Each outward step multiplies distance beyond ordinary intuition. Speed increases slowly. Distance explodes outward. Human technology offers a clear example. Over centuries, we have increased travel speeds from walking to horseback to steam engines to aircraft to rockets. Each improvement feels dramatic. Each advancement compresses travel time across familiar distances. Yet even our fastest spacecraft move at only a tiny fraction of light speed. The gap between human speed and cosmic speed is enormous. Even so, the gap between light speed and cosmic distance remains vast. This reveals something subtle. Distance in the universe grows far faster than speed ever has. Within our daily lives, doubling speed can cut travel time in half. Across cosmic distances, doubling speed barely changes the experience. Even multiplying speed many times would leave the galaxy stretching across thousands of years of travel. The imbalance becomes clear when we think in terms of scale. Imagine increasing speed tenfold. A journey that once took 100,000 years would still take 10,000 years. That remains longer than recorded human history. Increase speed 100-fold, and the crossing would still span 1,000 years. The arena is simply too wide. Space itself adds to this imbalance. It is mostly empty. There are no dense corridors of stars to bridge distance quickly. Between one star and the next lies darkness and vacuum stretching across trillions of kilometers. Between galaxies lies even more emptiness. The universe does not cluster tightly enough for speed to feel triumphant. This is why light speed feels slow only when we widen the frame. Against a planet, it is overwhelming. Against a star system, it is impressive. Against a galaxy, it is steady. Against the observable universe, it becomes a boundary rather than a conqueror. Vastness changes everything. When scale becomes immense, the meaning of speed transforms. The fastest possible motion becomes something measured, something enduring, something patient. Light does not weaken at larger scales. It does not lose energy or determination. It continues at its constant pace, unwavering and precise. The only change lies in the stage upon which it moves. Speed remains fixed. Distance expands beyond instinct. When the stage grows wide enough, scale quietly overpowers velocity, and it does so without resistance. Between the stars, there is mostly nothing. When we look at the night sky, it can feel crowded. Points of light scatter across darkness. The Milky Way appears as a soft band filled with distant suns. From Earth, the universe can seem rich and full. Yet that appearance hides a deeper truth. Stars are very far apart. Our nearest stellar neighbor, Proxima Centauri, sits more than 4 light years away. That is trillions upon trillions of kilometers of separation. Between our sun and that star lies mostly empty space. Empty space is not dramatic. It contains faint traces of gas, scattered particles, and drifting radiation. But compared to the density of matter on Earth, it is almost nothing at all. The vacuum between stars is so thin that even the best laboratory vacuums on Earth contain more particles per cubic centimeter. The space between stars is vast and quiet. Inside galaxies, stars may appear clustered when viewed from afar. Spiral arms curve gracefully around galactic centers. Yet even within those arms, the separation between stars remains immense. If the Sun were the size of a grain of sand, the nearest star would still sit several meters away. Most of the space between them would be empty. Galaxies contain billions of stars. They also contain enormous gaps. Between galaxies, the emptiness grows even more profound. Intergalactic space holds far fewer stars and even thinner gas. Galaxies drift within enormous volumes of near vacuum, separated by millions of light years. Travel across these regions would involve crossing mostly nothing. Light moves steadily through this emptiness. It encounters little resistance. It does not slow down because of friction. It does not lose momentum. It simply moves forward at its fixed pace. Yet the emptiness adds to the feeling of slowness. There are no intermediate landmarks to break the journey. No bright stepping stones between destinations. The path from one star to another crosses long stretches without change. The journey feels extended because the distances are so uninterrupted. If stars were tightly packed, travel might feel more achievable. If galaxies overlapped closely, the scale might feel compressed. Instead, the universe spreads its structure thinly across enormous volumes. The Sun itself occupies only a tiny fraction of the space within our solar system. Most of the solar system is empty. Planets are separated by millions of kilometers of space. Asteroid belts are mostly void, with vast distances between individual rocks. Scale increases as we step outward. Within the Milky Way, stars orbit the galactic center at large separations. Even in regions where stars are relatively dense, they remain far apart compared to their sizes. The galaxy's beauty lies in its structure, yet its substance is distributed across a wide, sparse volume. This sparseness contributes to the impression that light speed feels insufficient. Light travels without resistance through vacuum. Yet because the distances are so large and so empty, it must simply continue moving for years, centuries, and millennia before reaching its destination. The emptiness does not slow light down. It simply extends the journey. Imagine crossing a desert that stretches beyond the horizon in every direction. The walking pace may remain steady, but the lack of landmarks and the uninterrupted expanse make the journey feel longer. In space, that desert extends across trillions of kilometers. Between galaxies, that desert stretches across millions of light years. The vast majority of the universe consists of vacuum. Matter forms islands within an ocean of emptiness. Stars cluster into galaxies. Galaxies cluster into groups and filaments. Yet between these structures lie enormous voids. Some of these cosmic voids span tens of millions of light years across. They contain very few galaxies. They are regions where matter is sparse and separation dominates. Light crosses these voids faithfully. It does not hesitate. It simply travels. The feeling that light speed is slow emerges not because light lacks power, but because the emptiness it must traverse is immense. There is simply so much of it. When we imagine travel across the galaxy, we might picture moving from star to star. In reality, most of the time would be spent crossing darkness. The stars themselves are small targets within a wide sea of vacuum. The universe is structured, yet it is also sparse. This sparseness magnifies distance, it amplifies scale, it stretches the time required for even the fastest motion. Emptiness carries weight in its own way. It expands separation. It deepens silence. It lengthens journeys. Light moves steadily through that silence. The emptiness remains. There is another layer to this story. Until now, we have imagined distance as something fixed. We pictured stars separated by vast gaps, galaxies floating apart in quiet space, and light traveling steadily across those spans. Yet space itself is not still. The universe is expanding. This does not mean galaxies are flying outward through empty space like fragments from an explosion. It means that space itself stretches. The fabric that holds galaxies in place gradually grows larger over time. The distances between distant galaxies increase because the space between them expands. This expansion has been occurring for billions of years. When the universe was young, galaxies were closer together. Over time, space stretched, and the gaps between large structures grew wider. Light traveling across those gaps did not simply cross a static distance. It crossed a distance that was slowly increasing while it traveled. This changes the meaning of scale. If you send a beam of light toward a very distant galaxy, that galaxy is not standing still. The space between you and that galaxy continues to stretch. Light moves forward at its constant speed, yet the target may drift farther away while the beam is en route. In some cases, that stretching is so strong that the distance increases faster than light can close it. This statement can feel surprising at first. We are taught that nothing moves faster than light. That rule remains true. No object moves through space faster than light. However, space itself can expand without breaking that limit. When we say a distant galaxy is moving away from us faster than light, we are describing the growth of space between us, not the galaxy racing through space at impossible speed. The galaxy remains within its local region, obeying the same physical laws. The stretching occurs across vast cosmic scales. Because of this expansion, there are regions of the universe whose light will never reach us. Even if a galaxy shines brightly, even if it emits light continuously, the space between us may expand so steadily that its light can never overcome the growing separation. The light moves forward, but the destination recedes. In this way, light encounters a deeper limit. It is not simply crossing fixed emptiness. It is crossing space that continues to widen. Imagine standing on a long walkway that is slowly extending beneath your feet. You walk forward at a steady pace. If the walkway stretches slowly, you will still reach the end. If it stretches faster than you walk, the end will drift away from you indefinitely. Light walks across expanding space. For nearby galaxies, expansion is modest enough that light can cross the gap. For very distant regions, expansion dominates. This introduces a quiet boundary to the universe. There exists a cosmic horizon beyond which events cannot influence us, because light from those regions cannot close the expanding gap. That horizon is not a wall. It is a limit shaped by speed and expansion together. The universe continues to grow larger. Space continues to stretch. Galaxies drift farther apart over time. Light does not slow down. It remains constant and steady. Yet the stretching of space means that some distances increase, even as light travels. This dynamic reshapes the question we began with. Why does light speed feel slow? Because the stage itself is not fixed. The universe is not a still arena waiting to be crossed. It is a living structure that grows. The farther outward we look, the more expansion contributes to separation. Light speed sets a maximum rate of travel through space. Expansion modifies the distances that must be crossed. The combination creates limits to connection. When we observe distant galaxies, we see them as they were billions of years ago. Some of them may already lie beyond our cosmic horizon. Their present light may never reach us. We remain connected only to the portion of the universe whose light has had time to arrive. The expansion of space adds depth to scale. It is not only that distances are immense, it is that those distances are increasing over time. The universe gently drifts outward in every direction, stretching the fabric that light must cross. The fastest possible speed remains steady. The arena continues to widen. Light moves forward without hesitation. The universe expands quietly beneath it. And in that quiet stretching, new horizons form. There is a boundary to what we can see. It is not a wall. It is not a sharp edge. It is a limit shaped by time, distance, and the steady pace of light. This boundary is often called the cosmic horizon. The cosmic horizon marks the farthest distance from which light has had enough time to reach us since the beginning of the universe. It is defined by travel time. Light has been moving for about 13.8 billion years. During that time, space has expanded. The region from which light could reach us has grown into a vast sphere about 93 billion light-years across. Everything inside that sphere lies within our observable universe. Everything beyond it remains unseen. The horizon does not mean the universe ends there. It simply means that light from beyond that distance has not reached us yet. There may be galaxies, stars, and entire structures extending far beyond our observational boundary. We remain unaware of them because their light has not bridged the gap. Light speed defines this limit. If light traveled faster, the horizon would extend farther. If light traveled slower, the horizon would shrink. The size of the observable universe is tied directly to the speed at which light carries information. This horizon exists for every observer. An observer in a distant galaxy would have their own cosmic horizon centered around them. Their observable universe would include regions we cannot see and exclude some regions we can. The universe does not revolve around any one position. The horizon simply marks the limit of connectivity for each location. The idea can feel abstract at first. We are used to thinking of sight as something straightforward. If something exists and emits light, we expect to see it. In everyday life, distance may blur detail, but it does not erase visibility entirely. On cosmic scales, distance can erase visibility altogether. There are regions of space so distant that even light from their earliest moments has not reached us. There are galaxies whose present light will never reach us because expansion carries them farther away than light can travel across the growing space. Some regions will remain forever beyond observation. This does not mean they are unreal. It means they lie beyond causal contact with us. No signal sent from Earth today can reach them. No signal sent from them today can reach us. The horizon creates a sphere of influence. Within that sphere, events can affect us because light can carry information across the distance. Beyond that sphere, events unfold independently, disconnected from our observation. The cosmic horizon introduces humility. The universe may extend far beyond what we can detect. Our telescopes grow more powerful with time. We peer deeper into space and further back into history. Yet there will always remain a limit defined by light's travel time and cosmic expansion. Even the fastest signal possible cannot erase that boundary. This reveals something subtle about knowledge itself. Everything we know about the cosmos arrives through light or other signals traveling at light speed. Our understanding is shaped by what has had time to reach us. The horizon marks the edge of available information. It does not limit imagination. It does not limit existence. It limits connection. When we look at the night sky, we are looking within our observable bubble. Every star and galaxy we detect lies inside that sphere. Beyond it lies more structure, perhaps endless in extent, yet disconnected from our view. The horizon moves as time passes. As the universe ages, light from slightly farther regions may reach us. Yet expansion also carries distant regions away. Some areas that were once visible may drift beyond reach in the far future. The boundary is dynamic. Light speed defines what is reachable. Expansion defines how that reach evolves. The cosmic horizon is not dramatic. It does not announce itself. It is simply present, woven into the structure of space and time. It reminds us that even with the fastest speed in existence, there are limits. Reality extends beyond observation. Mystery remains beyond the horizon. After traveling outward across planets, stars, galaxies, and horizons, a quieter question begins to form. Why is there a limit at all? Why does light move at a fixed maximum speed instead of moving infinitely fast? The answer rests in the structure of spacetime itself. Light speed is not simply a high number. It is woven into the fabric of reality. It acts as a constant that links space and time together. In the equations that describe how the universe behaves, this constant appears again and again. It does not emerge from technology or measurement. It emerges from structure. When something moves through space, it also moves through time. These two motions are connected. The faster something moves through space, the slower it moves through time relative to other observers. This relationship becomes noticeable only at very high speeds, but it is always present. Light moves at the maximum possible rate through space. Because of this, it experiences no passage of time along its own path. From the perspective of light itself, the journey from a distant galaxy to Earth involves no ticking clock. For us, that journey spans billions of years. For light, the path is immediate. This reveals how deeply speed and time are connected. If light speed were infinite, time and space would behave very differently. Information could travel instantly across any distance. Cause and effect could blur together. Events separated by vast space could influence each other without delay. The finite speed of light prevents that. It ensures that signals require time to cross distance. It ensures that cause precedes effect in a consistent way. It preserves order. Imagine a universe where information moved infinitely fast. An event in one region could instantly affect a distant region. There would be no waiting, no delay, no gradual unfolding of influence. The structure of interaction would collapse into simultaneity. Instead, the universe unfolds step by step. Light speed creates a rhythm. Signals expand outward in waves. Events ripple through space at a steady pace. Nothing outruns that ripple. This allows structure to form. It allows stars to evolve gradually. It allows galaxies to interact over long timescales. The speed limit gives shape to reality. Even gravity respects this limit. Changes in gravitational fields propagate at light speed. If the Sun were to shift position, Earth would continue orbiting based on the previous configuration for about 8 minutes until the change in gravitational information arrived. This reinforces the idea that light speed governs influence itself. The finiteness of light speed also allows the universe to have horizons. It allows distant regions to remain temporarily or permanently beyond contact. It creates a layered structure of connection where proximity matters. If light speed were higher, those layers would stretch differently. If it were lower, they would compress. The particular value of light speed shapes the scale of everything we observe. Atoms, stars, galaxies, and cosmic expansion all unfold within the constraints set by this constant. Light speed acts as a framework. It ties together space and time into a single geometry. It determines how quickly energy and information can move. It defines the maximum pace at which events can influence one another. Without this limit, physical laws would not behave as they do. The stability of matter depends on electromagnetic interactions which propagate at light speed. The structure of atoms relies on relationships shaped by this constant. The formation of stars depends on signals traveling across gas clouds at finite rates. The universe's ability to organize into coherent structures rests partly on the fact that influence travels neither infinitely fast nor arbitrarily slowly. The limit provides balance. When we ask why light speed feels slow, we are measuring it against cosmic scale. Yet that same speed enables coherence. It allows stars to shine steadily. It allows galaxies to rotate with predictable dynamics. It allows time to flow in ordered sequence. Light speed is not arbitrary. It emerges as a structural feature of spacetime. It preserves causality. It preserves sequence. It preserves stability. It may feel slow against billions of light years, yet it defines the architecture of reality. Limits create order, and within that order, the universe unfolds quietly. To understand why light speed holds such a central role, we have to look more closely at how space and time connect. In everyday life, space feels separate from time. We think of distance as something measured in meters or kilometers. We think of time as something measured in seconds or years. They appear independent. Yet at high speeds, especially near the speed of light, space and time begin to behave as parts of a single structure. This structure is called spacetime. Spacetime blends 3 dimensions of space with 1 dimension of time into a unified framework. Every event in the universe takes place somewhere in space and at some moment in time. Together, those coordinates describe reality. Light speed links these coordinates in a deep way. When an object moves slowly, its passage through time feels steady. Its clock ticks normally. Its length appears unchanged. But as an object moves faster and approaches light speed, something subtle begins to happen. Time slows down relative to observers at rest. This effect is called time dilation. A clock moving near light speed ticks more slowly than a stationary clock. The faster the motion, the stronger the effect. At the same time, distances contract along the direction of motion. This effect is called length contraction. Objects moving close to light speed appear shorter along the direction they are traveling. These changes are not illusions. They are built into the structure of spacetime. Light sits at the boundary of these effects. Because light moves at the maximum possible speed, its relationship to time becomes extreme. From the perspective of light itself, time does not pass. A photon emitted from a distant galaxy and absorbed billions of years later experiences no duration along its path. For observers like us, billions of years pass. For light, the journey unfolds without time. This idea reveals how deeply light speed is woven into spacetime. The closer something moves to light speed, the more space and time adjust around it. Time slows. Length contracts. Energy increases. All of these changes preserve one constant. The speed of light remains the same for all observers. No matter how fast you are moving, you measure light traveling at the same speed. This constancy requires space and time to adapt. If 2 observers move relative to each other, they may disagree on how much time has passed or how long a distance is. Yet they will agree on the speed of light. Spacetime adjusts to preserve that agreement. In this way, light speed acts like a stitching thread holding the geometry of the universe together. It defines how far apart events can influence each other. It defines how time stretches and contracts. It shapes the causal structure of reality. Imagine spacetime as a vast fabric. Objects with mass bend this fabric, creating what we experience as gravity. Light travels along paths shaped by that curvature. Even when space bends around stars or black holes, light follows the geometry at its fixed speed. Light does not decide how fast to move. Its speed emerges from the nature of spacetime itself. This is why light speed cannot be exceeded. It is not merely a limit imposed by energy requirements. It is a structural feature of the geometry of the universe. If something with mass attempted to reach light speed, spacetime would respond by requiring more and more energy. The structure resists that crossing. The limit remains firm. Light speed shapes how the universe behaves on every scale. It determines how signals spread from exploding stars. It determines how gravitational waves ripple through space. It determines how particles interact at the smallest levels. The value of light speed sets the scale for cosmic relationships. Without this constant, time and space would not maintain consistent structure. Events could overlap in unpredictable ways. Causality could fracture. Instead, the universe unfolds with order. Light moves at its steady pace. Space-time adjusts to maintain that pace for every observer. Time stretches, length contracts, energy transforms, the limit holds. This interplay between light and spacetime explains why the speed of light is not just another number. It is foundational. It anchors how distances relate to time and how motion reshapes measurement. When we say light speed feels slow against cosmic distance, we are measuring it against scale. Yet that same speed defines the framework that allows galaxies, stars, and observers to exist coherently. Physics is woven into the fabric of spacetime, and light traces its threads. Imagine, for a moment, that the speed of light were different. Not infinite, not instant, just faster. Suppose light moved 10 times faster than it does now. Instead of traveling 300,000 kilometers per second, it would move at 3 million kilometers per second. Across Earth, that difference would hardly be noticeable. Light already feels instant on planetary scales. Making it 10 times faster would not change the feeling of flipping a switch or watching a sunrise. But what about larger distances? The nearest star, Proxima Centauri, sits about 4.24 light-years away. At 10 times light speed, its light would reach us in a little over 5 months instead of more than 4 years. That sounds dramatic. The delay would shrink from years to months. Yet the galaxy still stretches across about 100,000 light-years. At 10 times light speed, crossing the Milky Way would still require about 10,000 years. 10,000 years is twice as long as recorded human history. Entire civilizations would still rise and fade during a single galactic crossing. Even with a 10-fold increase in speed, the galaxy would remain immense. Now extend that outward. Andromeda lies about 2.5 million light-years away. At 10 times light speed, the journey would still require 250,000 years. That is longer than the entire span of modern human existence. Human societies as we know them have existed for only a fraction of that time. Millions of years would still pass when crossing intergalactic space. Push the adjustment further. Imagine light moving 100 times faster. Crossing the Milky Way would then take about 1,000 years. Crossing to Andromeda would take 25,000 years. These numbers feel smaller, yet they still stretch far beyond a single lifetime. The scale does not collapse easily. Even if light traveled 1,000 times faster, Andromeda would still require 2,500 years of travel. The observable universe, spanning tens of billions of light-years, would still remain staggeringly large. Speed can multiply. Vastness absorbs that multiplication. This reveals something subtle. When distances reach cosmic scales, increasing speed produces diminishing returns in perception. Each factor of increase compresses time somewhat, yet the remaining span remains immense. The universe is simply too wide. Its distances are measured not in thousands or millions of kilometers, but in millions and billions of years of light travel. A 10-fold or even 100-fold increase in speed would not erase those magnitudes. It would soften them, but not defeat them. Vastness does not shrink easily. It resists compression. Consider the observable universe, roughly 93 billion light-years across. If light were 10 times faster, the observable boundary would expand accordingly over cosmic time. Yet expansion would still stretch space. The horizon would still exist. There would still be limits shaped by travel time and cosmic growth. the arena remains immense. The feeling that light speed is slow arises from comparing it to distances that dwarf intuition. Making it somewhat faster does not remove that comparison. It only shifts the numbers. We might feel more connected to nearby stars. Conversations across interstellar space might shrink from decades to years. Yet galaxies would still stand apart by tens of thousands of years of travel. Intergalactic separation would still span hundreds of thousands or millions of years. The universe would still feel enormous. Scale dominates because it grows in layers. Planetary scale gives way to stellar scale. Stellar scale gives way to galactic scale. Galactic scale gives way to cosmic scale. Each layer multiplies distance dramatically. Even large increases in speed struggle against that layering. Light speed, as it exists, already feels overwhelming within our local environment. Against galaxies and cosmic expansion, it feels measured. Increasing it by modest factors does not remove the fundamental imbalance between velocity and distance. The stage remains vast. Speed cannot defeat scale. And so the question shifts again. If making light faster does not collapse the universe into intimacy, what happens if we imagine the opposite? If light were slower instead? Now imagine the opposite shift. Instead of making light faster, imagine it moving more slowly. Not dramatically slower at first, just half its current speed. Instead of 300,000 kilometers per second, imagine it traveling at 150,000 kilometers per second. On Earth, the difference might feel small. Light would still cross a room almost instantly. It would still circle the planet in fractions of a second. Our daily experience would remain mostly unchanged. But once we step beyond Earth, the effects begin to grow. Sunlight would take 16 minutes to reach Earth instead of 8. The warmth on your skin would arrive with a slightly longer delay. Solar flares would take twice as long to be noticed. Communication with spacecraft in the outer solar system would stretch further. These changes might feel manageable at first. Yet as distance increases, the consequences become more dramatic. Proxima Centauri would sit more than 8 years away in light travel time instead of 4. A simple exchange between Earth and a planet orbiting that star would stretch into 16 years for a single round trip. Across the Milky Way, crossing time would expand from 100,000 years to 200,000 years. Intergalactic journeys would stretch into even greater spans. Communication would slow even more deeply. The silence between stars would lengthen. The patience required for interaction would intensify. Yet the implications extend beyond travel and conversation. The speed of light is woven into the structure of atoms. Electromagnetic forces, the forces that bind electrons to atomic nuclei, propagate at light speed. These forces determine the size of atoms and the behavior of chemistry. If light moved more slowly, electromagnetic interactions would unfold differently. Atoms might become larger or less stable. Chemical reactions could proceed at altered rates. The delicate balance that allows matter to organize into complex structures could shift. Stars depend on similar balances. The fusion reactions inside stars are governed by physical constants that include light speed. If light traveled more slowly, energy would move outward from stellar cores at different rates. The stability of stars might change. Their lifetimes could shorten or lengthen in unexpected ways. galactic evolution could unfold differently. Cosmic history would compress in unusual ways. Because light links distance and time, slowing it would alter how we observe the universe. A galaxy 1 billion light-years away would appear as it was 1 billion years ago, only if light retained its current pace. With a slower speed, the same physical distance would correspond to a longer travel time. Our view into the past would stretch differently. The cosmic horizon would shrink. If light moved more slowly, the observable universe would be smaller. Light would not have had enough time to cross as much distance since the beginning of cosmic expansion. Our sphere of awareness would contract. Regions that are visible today might lie beyond reach in a slower light universe. Life itself might struggle to form under altered constants. The stability of matter depends delicately on the interplay between electromagnetic forces and quantum behavior. If the speed governing those interactions shifted significantly, atoms might not hold together in the same way. Molecules might fail to form reliably. The chemistry that supports life could falter. Even modest adjustments to fundamental constants can produce large changes in cosmic structure. Light speed, as it exists, allows stars to shine steadily for billions of years. It allows galaxies to evolve gradually. It allows atoms to maintain stability. Slowing it too much could disrupt those balances. The universe might still exist, but it would feel different. It might be dimmer. It might be quieter. It might be structured in unfamiliar ways. Communication across space would slow dramatically. Travel would become even more prolonged. The cosmic horizon would tighten. The layers of history visible to us would compress. The sense of vastness would remain, yet the reach of influence would shrink. The current value of light speed occupies a middle ground. It is fast enough to allow complex structure and wide horizons. It is slow enough to preserve order and sequence. It balances interaction and separation. When we imagine it slower, we begin to see how delicately tuned this constant is within the architecture of reality. Light speed does not merely set a travel rate. It shapes atoms, stars, and galaxies. It defines how far influence can extend and how time layers across distance. If it were slower, the universe would not simply feel more patient. It would feel different at every scale. Light speed balances the universe delicately. After stepping through physics, expansion, atoms, and horizons, it helps to turn inward. The question we began with, why does light speed feel slow, is not only a scientific question. It is also a perspective question. The universe is not small. We are small within it. That difference shapes how speed feels. On Earth, we experience distance in human terms. A walk across a park feels moderate. A drive across a country feels long. A flight across an ocean feels significant. Our emotions respond to time and distance in ways shaped by daily life. When something happens instantly, we feel immediacy. When something requires waiting, we feel delay. Light rarely makes us wait in everyday life. Flip a switch and the room brightens. Step outside and sunlight meets you. Look across a field and the scene appears without noticeable pause. Because of this, we associate light with instant presence. Then we widen the frame. 4 years to the nearest star. 100,000 years across our galaxy. millions of years to nearby galaxies, billions of years across cosmic scale. The same speed suddenly feels patient. What changes is not light. What changes is scale. When we compare light speed to the size of the universe, we are comparing a constant to something almost beyond measurement. The universe spans distances that dwarf instinct. It unfolds across time spans that stretch beyond memory. Light feels slow only against infinity. If the universe were small, if galaxies were separated by modest distances, light speed would feel unstoppable. There would be no tension. There would be no horizon. Everything would sit within immediate reach. Instead, the universe stretches outward in every direction. This stretch invites humility. We often imagine speed as power. The faster something moves, the more dominant it feels. Yet against cosmic vastness, even the ultimate speed becomes part of a larger picture. It moves steadily, yet the arena remains immense. That realization can feel unsettling at first. It reminds us that much of the universe lies beyond immediate connection. It reminds us that even the fastest signal cannot compress all distance into closeness. Yet it can also feel calming. Vastness reframes urgency. The universe unfolds across billions of years. Galaxies drift patiently. Stars evolve over immense spans of time. Light carries information across distances that take longer than civilizations endure. In that context, human time feels brief and delicate. The emotional shift emerges quietly. We are not standing in a small, crowded cosmos waiting to be crossed. We exist within a structure so wide that even light requires eras to traverse it. The feeling that light is slow reflects how large the stage truly is. Perspective changes understanding. When we focus on speed alone, light appears supreme. When we focus on distance alone, the universe appears immeasurable. When we hold both together, the tension becomes clear. Light is extraordinary. The universe is immense. The impression of slowness is born from that pairing. We often measure importance by immediacy. What happens quickly feels urgent. What takes years feels distant. Cosmic scale dissolves that habit. It reveals processes unfolding far beyond personal timelines. The universe does not rush. Stars shine steadily for billions of years. Galaxies rotate across vast cycles. Light travels faithfully through empty space without hesitation. Against that backdrop, the idea of slow begins to soften. Light speed feels slow only because infinity stands behind it. We are small observers inside a structure that exceeds intuition. The contrast between our scale and cosmic scale shapes perception. When we encounter distances measured in millions or billions of light years, our internal sense of proportion stretches. The realization is not dramatic. It is quiet. The universe is not failing to be reachable. It is simply wide. Light remains constant. It remains extraordinary. It defines the limits of influence and connection. It carries history across time. Vastness reshapes how that constancy feels. And in that reshaping, perspective deepens. Humility settles gently. We are participants in a cosmos whose scale invites reflection rather than conquest. Let that reflection rest quietly within you. Light does more than illuminate. It draws borders. Not physical borders that you can touch, but boundaries woven into reality itself. The speed of light defines what can influence what. It defines what can be known. It defines what can be reached. Light speed is not just motion. It is a line. Everything that happens in the universe spreads outward at or below that line. Signals travel. Gravity ripples. Energy moves. Nothing outruns it. This creates a structure of reach. If something lies close enough, its light can reach you. If it lies too far away, its light has not yet arrived, or never will. That is a boundary. Light speed defines knowledge. Everything we know about the universe arrives through signals moving at light speed. When you look at a star, you are receiving information carried by photons. When astronomers study distant galaxies, they are reading ancient light that has crossed billions of years. If light cannot reach us from a region, we cannot observe it. Our knowledge expands outward only as far as light has traveled. This boundary is subtle. It does not feel restrictive when we look at the night sky. It feels open and expansive. Yet there are entire regions beyond what we can ever see, not because they are hidden, but because they are beyond contact. Light speed defines connection. If two events lie within each other's light cones, meaning light has had time to travel between them, they can influence one another. If they lie outside that reach, they remain causally separate. This shapes the structure of the universe. Galaxies that drift beyond our cosmic horizon no longer share future interaction with us. Their light fades from reach. Their stories continue, but disconnected from ours. The boundary moves with time, yet it persists. Light speed defines possibility. Travel across space cannot exceed this limit. Communication cannot outrun it. Exploration is shaped by it. Even imagination must acknowledge it when grounded in physics. The boundary does not imprison. It defines the rules of engagement. Within the limit, stars can form, planets can orbit, life can evolve, signals can travel, cause leads to effect in ordered sequence. The speed of light preserves that order. Without the boundary, influence would blur across distance instantly. Cause and effect could overlap in confusing ways. The separation between events would weaken. The boundary creates clarity. It gives the universe shape. Imagine drawing a circle around yourself representing everything that can influence you at this moment. That circle expands as time passes because light from farther distances arrives. Yet beyond that expanding circle remains an outer region untouched by interaction. The boundary shapes experience. When we ask why light speed feels slow, we are brushing against this boundary. We are sensing that reach has limits. We are noticing that connection requires time. The feeling of slowness arises when we compare our desire for immediacy to the reality of separation. Yet the boundary is also protective. It ensures that the universe unfolds in layered fashion. It allows regions to develop structure independently. It allows time to progress in consistent order. Light speed draws a clean line between before and after, between reachable and unreachable, between influence and isolation. This line gives meaning to distance. It gives weight to time. It gives the universe dimension. Without a boundary, everything would collapse into instant connection. With it, the cosmos gains depth. Galaxies separated by millions of light years remain distinct. civilizations separated by decades of light travel would experience silence between exchanges. The pause carries significance. Light speed does not limit existence. It limits contact. And in doing so, it defines how stories unfold across space. The universe becomes a tapestry of regions connected by light's steady pace. Each thread stretches outward at the same speed. Each interaction waits its turn. Boundaries create meaning. Light is not only brightness, it is the edge of what can be reached. And within that edge, reality takes shape. We began with a simple question. Why is light speed so slow? At first, the question feels almost absurd. Light moves at 300,000 kilometers per second. Nothing with mass can reach it. It circles Earth more than 7 times in a single second. It feels absolute, untouchable. And yet, when we widened the frame, something shifted. 4 years to the nearest star, 100,000 years across our galaxy. Millions of years between galaxies, billions of years across the observable universe. The speed did not change. The scale did. Light feels fast close to home. It feels slow across cosmic distance. That tension is not a flaw in light speed. It is a revelation about the size of the universe. The universe is vast beyond intuition. We evolved on a small planet, orbiting an ordinary star, inside one galaxy among trillions. Our brains learn to measure distance in steps and seconds. Against that background, light feels instant. But against billions of light years, even the ultimate speed appears measured. Light speed is steady and constant. It defines causality. It shapes atoms. It governs stars. It draws the cosmic horizon. It weaves space and time into a single structure. It preserves order. Vastness is what changes perception. When we compare light speed to the immensity of the cosmos, we are really confronting the scale of reality itself. We are recognizing that the universe is not arranged for convenience. It unfolds across distances that dwarf our lifetimes. And yet, there is something quietly beautiful in that realization. Light connects us to the past. When you look at a star, you are seeing history arrive. When astronomers study distant galaxies, they are reading ancient chapters written in photons. Light may feel slow across the universe, but it faithfully carries stories across billions of years. Without that steady pace, the universe would lose structure. Without that limit, cause and effect would blur. Without that boundary, knowledge would not have shape. For us, as humans, this perspective does something gentle. It softens urgency. It reminds us that we live within a cosmos far larger than our daily concerns. It reframes impatience. It highlights humility. We are small within the universe. That smallness is not weakness. It is context. The same light that struggles across galaxies also warms your skin in 8 minutes from the sun. It lets you see a friend's face across a room. It carries the glow of distant stars into your eyes tonight. It is fast enough for life, slow enough for structure, steady enough for meaning. So when we ask why light speed is so slow, we are really asking why the universe is so wide. And the answer is quiet. Light is not slow. The universe is immense. Let that immensity settle gently in your thoughts. Let the scale of it all stretch outward beyond imagination. And rest for a moment. inside the vastness.